Hello, it's Duncan. Loyal viewer David had a lot of questions in the comments to the last video, where we learned to compose higher order functions to create HTTP 4K request handlers. He liked the idea, but was worried about the performance of calling business logic that used coroutines from the non-suspend handlers. This got me wondering whether Project Loom and Java virtual threads make this a non-issue. So today I'll start by looking at why operating system threads limit the throughput of our servers, and how virtual threads solve that problem. Once we have that working, then we can use more virtual threads to invoke suspend functions from plain old functions. With Project Loom, I think we really can have the best of both worlds, and that I have the benchmarks to prove it. I want to start by looking at the throughput of an HTTP 4K server. So I set up this throughput tests, and I'm going to use it to call a fast function here. And all that does is return the length of the string that is passed. And using the handler for that we wrote last week, we can convert that into an HTTP handler like this. We can say that our handler is a handler for, and now we need to give it the reference to the function, which is fastFun. We then say extracting from the query string. So we can say the lens is the query dot required. We'll give it the name of S, I think, just for a string. And now we need to tell it how to convert int into a response. So that's going to be on success is int to response. And I think I'm going to use a lambda in there, and we'll just say that if I take the int, then I can return a response. Well, the new IntelliJ single line completion seems to work quite well. It's saying you want a response with 200. Well, I don't think it's quite right, but pretty close. We wanted a response with a status of OK, and the body wants to be the int toString. We could have used a lens, but I'd have had to work out how to map an int into a string. So the type of this thing is request a response, which is HTTP handler. And now the beauty of HTTP 4K is that I could just call that in memory, but actually what I want to do is create a server out of it. So I can say something like handler.aServer. You need to give it a server config. Let's use Jetty. So that's going to be Jetty 11 on some sort of port. We'll call it 8080. And we're going to start that server. Now then, I can shut down that server when I'm done if I use a use block. So it's like that. And this is my server in here. Now our server's running. Let's get ourselves a client. So this is going to be val client is, and I think I've got OK HTTP lying around. That's that. And now I can ask my client to process a request with a method of get. We also need to tell it the URI. So that's going to be HTTP localhost 8080. And as we don't have any root set up, any root will hit this handler. Don't know what handler's doing there, but we can then say I want a query of S to match the thing we're extracting up here, and then we're going to give that the value of banana. Now that will give us response, and we can assert things about that response. So I'm going to say assert equals 200 is response.status. That's good. Although I think actually response.status is an object. Yes, it is. So in fact, that should be status.ok. And that the response's body should be the number of characters in banana, which is 6 as a string. Well, it's a lot of typing. Let's see whether it works. Run the throughput tests. Okay, well it doesn't look as if I've got a Jetty 11, and that makes me wonder why I'm using Jetty 11 rather than just Jetty. So let's undo that, and I'm going to go to our build Gradle file and add a dependency on test implementation org.httpk, and the thing I want is http 4k-server-jetty. Let's find out by importing. Good, and now that compiles, I think, and we can run. Okay, 2 seconds to do very little, but most of that will be starting up a server, I should think. And we passed, which is good. And let's just check we are doing the right thing by failing. Splendid. tidy this up a bit by taking that back to 6, and I think we can use the client to close that as well. So this would be client in here, and then move all these into there like that. Run. Okay, so that was a single request. How can we make OKHTTP make multiple requests at the same time? Well, one way is to set up an executor. So we can say executor, and you see we can give an executor's new single thread executor. I don't think I want that, but I will take executors dot, and here's the magic. We're going to use new virtual thread per task executor, because this is Java 21 and we can use Loom virtual threads. Now then, we can ask that executor to execute a block of code for us, and the block of code we want to execute is this stuff here. So we can say executor dot submit, and the block of code we're going to submit is all this lot here. And now what we can do is we can close down the executor. So we can say executor shutdown, and shutdown will try to run everything that's been submitted to the executor. Let's just run that and see what happens. Okay, it's good, but I'm going to take some convincing that everything is fine. First thing I'm going to do is I'm going to say executor dot await termination, and I'm going to wait, say, 30 seconds. And this returns a boolean that tells you whether it timed out or not. So it says here true if terminated. So if we go back here, we should say assert true executor terminated. And that will tell us whether we managed to run all the things that were submitted to us within the 30 seconds. How will we know that we ran anything at all? Well, that's a good question. What I think I'm going to do is I'm going to convert this to a block body, and I'm going to keep a count of how many times this has been invoked. Now we're going to be running this on a server, this Jetty here, which is multi-threaded. So we can't just set up a counter, but what we can do in here, we could say, I've got a private val invocation count, and that's going to be an atomic integer starting at 0. And in here, I'm going to say invocation count, get an increment. And once this is run, it starts at 0. Well, let's just check that. So in here, we're going to say assert equals 0 is the invocation count get. And down here, we'll say once all this is finished, then we should have seen one invocation. And we did. Now then, one invocation isn't very exciting, but we could submit more than one job to the executor. And so we could say, let's give ourselves a range from 1 to 1,000, and then every time we will submit a job to the executor. So now we expect at the end 1,000. Well, I'm going to leave one in there just to check that we do fail. And we do. We expected 1 and we've got 1,000. But those 1,000 things are happening reasonably simultaneously. Run that. Now the total time to run has been 2 seconds, but we know it took some time to set up Jetty. So I think what I want to do is keep track of how long it actually takes to submit all these jobs and have terminated the executor, which is to say, have run them all. So I think I'm going to be a bit cheeky. I'm going to say in here, we're going to set a variable which is start time milliseconds is system current time millis. And I'm going to make a property in this test. And we need to initialize it with something, so I'm going to initialize it with 0. And when we're done, we will remember the end time, and we've awaited termination, so the end point will be here, and we're going to say end time milliseconds is at this point, system time millis. And again, we will create a property and default it to 0. And now in order to see that, at the end, once we've done all of our testing, I'm going to write an at after each fun. I'm going to call it report, and it is going to say println. Well, actually the invocation count is the thing I want to print, so let's just say that plus, now we want to know how long it took. Duration milliseconds is the end time milliseconds minus the start time milliseconds, So we'll say duration dot of millis, where subtract those two. And then we'll put that in here as duration milliseconds, but it's not duration milliseconds, it is duration. And I guess we'll put that all in a string like that. See what we get. So in our output, we can see that we got 1,000 requests in roughly half a second. And with a little bit of work, we can report the request per second like that. So let's have a look. There we are. We're running nearly 2,000 requests a second. Not bad. Now, actually, our jobs here won't be finished until we've done this assert equals. But also, if any of these failed, we might lose that failure because we're running them on a different thread. So what I think I'm going to do is we're going to make this a callable rather than a runnable in here. And that will take that block and then that brace, I think, like that. And now I'm going to map in here. So if I say map, then what we end up with in here is list of future of unit because of these assertions which return unit. What we can do instead, I'm just going to comment these out, or take them away and comment them out. So we're going to wait for all that to happen. Put those down there, and now we are going to yield this response from the callable. This will make this a future of whatever this is, which is a response. And now I'm going to let that out of our OKHTTP use. So I'm going to say that if I take that out of there and put it there, it should still be true. So these are my futures, and once I've shut down the executor, waited for everything to happen and recorded how long it took to happen, I can go through those futures and check that the responses are all as we expected. So here we can say futures for each and move this up into there. Now we have to get on a future, so val response is it, the future, dot get, and we can make those assertions. And finally, we think that every one of these futures should already be done because we waited for the executor to terminate. So I'm going to say assert equals, it is done. There you go. Splendid. Right, I'm just going to do a little bit of work to separate out this bit of testing from the actual thing we're testing. So I think if we were to pull this thing out as a variable, we could move it all the way out here, and that would be our request. And I'm also going to pull this little block of code here out. So this is going to be val assertion, and that's going to be a lambda, these two things in it. I'm going to say assertion, we're going to run, and then we're going to pass the response in. So that is the subject of our assertion. A little bit of complaint that it doesn't know this is a response. And here we can say response. And now we can pull this thing out of here and up into here. And then inline that. And then finally, I think this 1000 and that 1000 are the same 1000. So we'll make a variable out of this in here, and this is going to be request count. So now we've got a setup up here, and I think we could reasonably move that down there. Run that. Good. And now I think that all of this would make a method that is, I'm going to call it run lots. So given a handler, a request, and an assertion, we can run lots of times by creating a server, running it up, and a client, and using the client to make actual requests, where we get around 2,000 requests a second. Okay then, a little bit of light inlining. I think we will add the parameter names to everything. We'll inline that, and we can inline that. Good. Okay, so 2000 requests a second for a function that runs really fast. What about a function that runs less fast? Let's duplicate all of this. Let's take that and we will put it down here, and I'm going to call this slow fun. And all this is going to do is it's going to say thread sleep for a second, and then it's going to return what fast fun did. And this is going to be test fast fun, and this will be test slow fun, and in order to be test slow fun, it's going to call slow fun extracting. And so the question now is, how fast should that run? Well, we'll run all the tests. And there's our answer. Now, obviously, this is 10 times slower, but I'm less interested in that than the fact that it took over 6 seconds. In the perfect world, we made 1,000 simultaneous requests, and each one of those waited 1 second. So in that perfect world, we really could have finished everything in 1 second, plus a little bit of parsing. Instead of which we took 6 seconds, and the reason for that is that our server only has a limited number of threads to process requests. I don't know what the number is, it will depend on the server, but once all those threads are sitting waiting in this thread sleep, then the other incoming connections will have to wait for those threads to finish and return their int, after which new connections will be allowed. The server sets up a limited thread pool because threads are expensive, and if it just allowed 1 thread per request, no matter how many requests were coming in, it would run out of memory. But this is Java 21, we have virtual threads, and in fact Jetty will allow us to use them. So let us change this to Jetty Loom and see how we do. And there we go. Plain old Jetty took 6 seconds to process 1,000 requests, each of which waited a second. And Jetty Loom has taken 1.1 seconds to process 1,000 requests. So effectively it was running them all at the same time. And it can do that because virtual threads don't take up a lot of memory, so it creates a new one for every request as it comes in. To help us interpret this, what I'm going to do is I'm going to go to the report, here you are, and ask JUnit to give us a test info, and then we'll use $testinfo.displayName as a prefix, like that. And now you can see what had what timing. And I think also I'm going to abstract the server. So if we take this thing, which is Jetty Loom, and give ourselves a val server config is : Jetty Loom. And it says it doesn't know which of these we're going to use, so I'm going to tell it that this is the function that takes an int and returns something Jetty Loomy, which is a Jetty, which is, goodness me, polyserver config, which is server config. Let's use that back here. So this will take a function returning a server config. I can then invoke the server config there. And now we're going to make a parameter out of that. Server config is good. Now we will move that up. And now we can have, what do we have? We have test fast fun, that uses Jetty Loom, but we could say fast fun normal Jetty by making that Jetty. We could then duplicate this as fast fun Loom Jetty, passing in Jetty Loom. This one is slow fun normal Jetty. If I make that Jetty, and we can have a copy of that that does slow fun Loom Jetty, and run them all. Okay, then here are the results. We can see that the slow function with normal Jetty is really quite slow, but using Loom Jetty we're running pretty much as if everything is in parallel. I'm a little bit suspicious, I must say, that these two numbers seem to be quicker than when we run them on their own. So just remember here 6,000 or 7,000 and we'll run fast fun Yes, run on its own, it's a lot slower, which suggests the hotspot is warming up on the first of our tests, which is the slow fun with no Loom Jetty. So it is going to look worse in comparison than I think it should. Also, I am seeing these issues here where we're getting a connection reset by peer when the client is trying to connect. I don't know why that's happening. It's a little bit worrying, but it only seems to happen on Loom Jetty when we're calling the slow fun. On a bit of a whim, I asked AI Assistant to explain the error message, and this is what it came up with. It says that the underlying TCP/IP connection is being unexpectedly closed by the server, and the number one reason is the server is overloaded. It correctly diagnoses that looking at my Kotlin code, it appears that we're trying to execute a large number of requests in a short period of time. And I guess, as it says here, the point of this really is to give us more requests than it can handle. But I don't think Jetty should terminate the connection prematurely. If I add a single retry in our executor here, just catching IO exceptions, printing the message and trying again, just once, let's try that. And look at our results. Well, you can see there we've got 6 actual errors, but a single retry was enough to make us succeed and in a sensible time frame. I'm just going to have a little refactor. And when I say a little refactor, well, that turned out to be quite a big refactor. So let's see what we've ended up with. We've ended up with some per test state, things like request count and the number of requests we want to make and the number of invocations we actually saw. And we've got a report object. The report object here captures the request count, the start and end time in milliseconds, and the errors from our run. And so now run lots is responsible for remembering the start and end time and capturing the errors in this synchronized list. From here, when anything goes wrong, we only retry once. And then down here, we build a report and we assign it to the field. And then this field is used in our after each, where we use the report to calculate the requests per second and show us the errors. And then I've extracted all the commonality here so that each one of these tests is itself a lot shorter. And we can see the structure. And that's using the static object and the companion object. And quite nicely we can use the query here and use it to populate our request as well as extract from our request in our handler. Okay, so if I run that, well, while we're doing this, I should note that I've added a very first test which runs the slowest one as a warm-up first. And here you can see our output. So the warm-up ran 1,000 iterations in 6 seconds with no errors. And then the other ones ran here. And you can see that we got running our slow function with normal Jetty took 6 seconds with no errors. Our fast function with normal Jetty took less than a second. We got 8,000 requests per second there. And then things started going wrong here. We got 96 connection resets when we ran the last 2 tests. But even with the retries, our slow function with Loom Jetty managed to run in just a little over a second, which, considering each one of the functions waits for a second, isn't bad. In other words, we have latency, but we still have high throughput. Now, obviously, it's not nice that we're getting these errors. And while I was refactoring, I noticed something, which is that the tests are run in sort of a random order. The first ones don't get any errors, and we get errors in the last set. In order to show that, we're going to take slow fun Loom Jetty here. I'm going to pin this tab so we can remember what we had. And then we'll go to slow fun Loom Jetty, the one's giving us all the errors, and move the test order of that one to be number 2. So number 1 is our warm-up. Number 2 is this one that was giving us a lot of errors, and then the others will be run in something like a random order. We do this, by the way, with this test method order annotation here. So let's run that. And here are the test results side by side. This was the previous run and this is this one. And you can see that slow fun Loom Jetty got a lot of errors when we ran it last, but slow fun Loom Jetty got no errors when we ran it first. So the errors very much seem to be getting worse as we go down through our tests. Now I wonder whether that's garbage collection, so let's close that and unpin that. And what I'm going to do is I'm going to say in our after all, which I think I called report. There we are. Once I've done everything, assuming everything is okay, we will garbage collect a couple of times to make sure that each test starts with a clean slate. Let's see if that makes any difference. And the answer is if it has, certainly not enough to stop us getting errors. Although notice this one has lots of errors now and this one has fewer, but they're bound to be random factors. It's interesting that we seem to overwhelm the later runs, but each time, when we call this run lots, we create a new server. It's handler as server, server config here. And in fact, we're closing the server once we're done here, so it will get rid of any resources that it uses. And in fact, I'm beginning to wonder whether we're overwhelming not our server, but the max TCP stack. That's a hypothesis, and maybe it would be better if we weren't to run every server on the same port. So I'll just go and make that happen. And here it is. So now we start the server on port 0, which means pick a free one. We have to update the requests URI to include the new port, but that's easy enough. And then we put the port into the report here so that we can see where it ran when we run it. So let's run it. Oh, and there's an interesting exception. We're getting unexpected end of stream when we're reading the request. Now I have seen these sort of things before, and they do tend to be that the operating system's TCP stack has just given up. I'm going to try running again. Okay, cutting to the chase. I can make the test always pass by retrying as many times as is needed. That's here. And every time we add to the errors so we can see how many we got in total. It doesn't seem to matter what order I run the tests in. And I have moved this clear the pipes function, which garbage collects just before we actually start everything we need to do. But no matter what I do, and what order I run the tests in, things seem to get generally progressively worse as we run the later tests. The only thing I found that can make it not error is if we sleep in here. And if I go all the way to 30 seconds, then we get no errors. So I don't know whether this is Jetty's problem, the JVM's problem, or the Mac's problem, but it does show that Loom is able to give us impressive throughput even with slow running responses. In this case here, we have 1,000 virtual threads waiting for a second with very little overhead. Okay then, I've taken out the sleep and run them again, and I'm just going to suck up the errors in order to get fast running tests, because now I want to look at coroutines. In reality, of course, our handlers aren't slow because they thread sleep. They're slow because they talk to a database or contact another web service or do some other sort of I/O. But virtual threads will be parked and not use up resources with I/O in the same way as they do here with this thread sleep. What though if we're calling coroutines code? If we have a coroutine that goes off and does some I/O, we can simulate that by saying this is a suspend fun, and we will call this slow coroutine fun, and we can't sleep. Certainly shouldn't sleep in a coroutine, but we can delay. Now, delay is part of Kotlin coroutines, which I don't think we're importing, so I'll just go and fix that. Import the Gradle stuff, and back to throughput tests, and now we should be able to import delay. And the compiler's confused, and so am I, because I needed to put suspend fun in there. There we go. So now we want a version of our test that calls slow coroutine fun instead of just slow fun. Let's find the one that calls slow fun with Jetty Loom. That's like this one. And let's duplicate that. Now we think we want Jetty Loom in order to handle as many requests as we possibly can. We'll make this 6 and we'll say slow coroutine fun Jetty Loom, and we just want to call slow coroutine fun. But now we have a problem, and that's that our extracting, we can see it here, takes a function from T to R, but not a suspend function from T to R. Now we could write a version of this that took a suspend function, but as you can see here, we can only call invoke on another coroutine, so we'd need to run blocking that thing. Also, it wouldn't compose, so what I think I'm going to do is I'm going to undo this and go back and say I could get this to compile if I had somewhere saying remove the suspendness on my slow coroutine function. Now obviously that doesn't exist, but let's make it happen. And I'm just going to accept all of these bits for now while we work out what we want. Okay, for this to work, it would have to take a suspend function from some t to some r, which is our f, and return a function from t to r. And we don't have those types, so we're going to add them in here. Fun, t, and r. And you see, if we had that, then this does compile. We just don't know how to implement it yet. But there is a way, and it's something like we say run blocking. This needs a coroutine context, and often we'd use dispatchers.io. The block that we want to invoke, which we don't really have because we need to return a lambda. So we need to return a lambda that takes a t, and given the t, we'll say run blocking, and we'll call our f on the t. Well, that compiles. Shall we try running it? Well then, that runs, and looking at the times, the throughput is effectively the same as our slow function that slept. Looking at what dispatchers.io does, well, it's the default I/O scheduler, and it's not immediately obvious, but I think this is effectively running on a thread pool with lots of threads because we think they're just going to be waiting on I/O. In our case, they're not actually waiting on I/O, they're waiting on that delay, so I'm not sure what's going on there. But in any case, with virtual threads, we can do better, because we can build a dispatcher from a virtual thread per task executor. And that's something like val loom dispatcher. And well, that completion was very nearly perfect, but this should be new virtual thread per task executor. And if we have one of those, then we can put that in here. We can say run blocking on this loom dispatcher. And then that will run our coroutine code on a virtual thread, and when it's parked on I/O, it won't be using a real thread. So let's run that. And there we go, and we effectively now have an infinitely big thread pool of virtual threads to run our coroutines on. And now we can complete the refactor by making this a parameter of remove the suspendness. And that's going to be called dispatcher. And I guess the type we really want is not executor coroutine dispatcher, but just coroutine dispatcher. And now if we make the receiver, then here we've got slow coroutine function, remove the suspendness. That's now not a great name. Maybe we can call it running on. And we can take these, cut them out of here, and then moving in to our mapping code. And back to our throughput tests, and make that public. And there we have it, HTTP 4K calling into a suspend function with no thread starvation because we're using virtual threads. There have been proof of concepts, but it's very hard to convert HTTP 4K to use coroutines. The problem is its fundamental abstraction is this HTTP handler here, and it's a function, but it's not a suspend function. The other abstraction is filter, and it too depends on HTTP handler, which is a function. Changing HTTP handler to be a suspend function then will be a huge breaking change. With Loom though, we don't need this function to be a suspend function in order to have high throughput. Servers like Jetty under Loom will just create virtual threads when running under Java 21, and they're as lightweight as coroutines. We can effectively have as many as we like. That means we can just use those threads, the virtual ones, to perform slow running tasks like I/O in our handlers without blocking operating system threads. And if we want to call suspend functions, which we can think of as the pre-Java 21 way of doing non-blocking I/O, then we can use this Loom dispatcher to wait for those to complete, again without blocking a real thread. I think the lesson I've learned from this is that introducing a handler for, which gives us a way to decouple HTTP 4K from our domain code, has allowed us to see that HTTP 4K itself doesn't really require coroutines. And again, function composition means that all of our handlers for and here and extracting are able to work with suspend functions if we convert them this way. Well, that was hard work. I hope it all makes sense. Thanks to David for his comment on the channel that inspired this work. You can see I'm writing tests here, but I haven't tried this in production. I'd really like to hear in the comments whether you can see any problems with it. If you'd like to see more of these sort of experiments, then please subscribe to the channel. Like this video so I know that it's the sort of thing you'd like to see more of, and maybe even buy the book that I wrote in that price called Java to Kotlin, a Refactoring Guidebook, details of which are in the show notes below. Thanks for watching.